as I told you, it's not so comfortable to be alone in the room, but anyway, let me start. In my study, you can find this presentation, which you already considered last time. And today we will go ahead, go in a little bit in depth on Laplace transform. Basically, it's a repetition a little bit, but for some aspects, I would like to say, but we will see the usefulness, how can it be used, the Laplace, in the context of dynamical systems. You remember I already told you about the definition. I would like to skip this part. I mean, this I already introduced last time. In any case, it's exactly what you know from, I don't know, math 2 or something like that. It's a parametric integral defined in this form, in which given a function f with some characteristics, this means should be integrable, no? In this sense. Let me say a reasonable function, roughly speaking, but of course, mathematically, probably you have seen something more in depth. For us, it's a signal, let me say. For us, it's a signal. We will see that with this definition can be we can analyze not only signal, or better to say with this structure, no? The Laplace transform. Let me say environment. Let me show a little bit to flesh out the idea. We will analyze also systems, and in particular dynamical systems. Okay, this we have already seen. I invested 2 lectures about the delta, and this we can skip directly, but I would like nevertheless emphasize this picture here in the lower part of the slide, in which we can see clearly the impulse response. I consider an input and a signal, which is delta, and I will obtain in output the impulse response or answer. I already told you a lot about it. We calculated this. Do you remember? We calculated for a system. This was an RC circuit. I don't remember. You can find everything in my study. But we calculated, let me say, indirectly. It's a way to do. Do you remember? Starting from the step answer. Here, the idea is I have an input which is delta, and I will have obtained an output which is depends on the system. At this moment, we are considering linear systems. Do you remember? The linear systems are characterized by this form. We can represent a dynamical system using matrix A, matrix B, matrix D, and initial conditions, depending on the dimension of the system. We have seen in detail this slide here, and the discussion. Do you remember? We discussed a lot about connection, let me say, between the delta impulse and the sigma, which is defined here. And also in this sense, we can speak about the unit step response, or in general step response. Do you remember? I told you about the step response, which with the amplitude 12, but the amplitude does not change qualitatively the answer, not just quantitatively, because the system is linear. We discussed a little bit this, but in any case, very important. We calculate it. We calculate it. Yeah, here we have a repetition of the concept of the Beck-Laplace transform. I don't want to insist on this abstract definition, because we will see that we will calculate the Beck-Laplace transform using a direct table. I will show you what I intend. But anyway, probably you have seen this definition in math, but just roughly speaking, Do you remember the Laplace transform was defined in the following way? Given in the function f of t, for us is a signal, no? But it's more concrete. I can associate in a complex function f of s. Here is exactly the Beck concept, no? The Beck Laplace transform. Given in the function fs, in a complex function, I can associate to this fs the corresponding f of t, no? The corresponding function which is defined in time. Now we can see interesting, nevertheless, also philosophically, we have a correspondence between a real function and an imaginary function. I don't have time now to go in depth on this concept, yeah, and vice versa, the imaginary function and the real function. This is nevertheless philosophically, let me say also mathematically, is extremely, I would like to say, fascinating. The reason we can think that we have a reality to be described, or do we assume to be a reality to be described, and to be described, to be analyzed. I would like to say something more, to be controlled. Sometimes it's useful to abstract the concept of in this case, of the signal, of the system. I would like to say of the reality, in order to obtain, we will see which one, in order to obtain some characteristics, in order to obtain some advantages, which we don't have if we attack, if I consider such kind of problems, control, just to analyze the behavior of a system, which we don't have in real analysis. Real analysis means in time. Time means considering the phenomenon or the phenomena in its time domain, exactly in the time which we observe, I would like to say. Okay, let me see. Just again, the definition, remember the exponential function of exponential up to s can be written in this form here, but it doesn't matter now. Here is again the Laplace transform. No? Is again the Laplace transform in which I am considering the variable s, the complex function variable s, consisting in two parts, and a real and imaginary one. Exactly what probably how we or how you know from high school, but from math it's clear. No? S is a complex variable which can be seen in imaginary part sigma plus j omega, which is the excuse me, sigma is the real part plus j omega, in which omega is the imaginary part. Just to look a little bit more explicitly the structure. I will come back on this later. Now, let me show you some possible Laplace transform, or some important Laplace transform of the signal, of some signals. In particular, let me start with sigma, and then we will go ahead with the rest. Sigma is exactly our step, unit step, because it's 1 multiplied sigma. Practically, from our point of view, it's important to remember to analyze, to model, I would like to say, the switch when the phenomena or phenomenon starts. We can see from here in time, as is defined. I received a question concerning delta. Delta includes sigma, because delta multiply sigma equal delta. I will come back on this. I received a question per email, which the question was related to the exercise of last time, in which I had, do you remember, delta in an input to our system, but I didn't put delta multiply sigma. The reason is delta multiply sigma is equal delta. We come back if you want. This means delta includes itself this representation, the mathematical representation of the switch. Do you remember, as I told you last time, delta multiply exponential function, this is again delta, no? Exponential, but delta multiply and f of t is again delta. Therefore, sigma is also the function. Delta multiply f of t is delta. Delta multiply sigma is again delta. Therefore, I didn't indicate. But we discussed before, no, a little bit, the delta multiply exponential, delta multiply the function. Okay, let me now calculate. We calculate some of some Laplace transforms of the most of some signals, and then I will. In any case, I know that you already know this part here, but to repeat a little bit, the exercise is to calculate an integral, basically. Now, look, in accordance with the definition, do you remember the definition is given a function f of t, the Laplace transform of this function f of t is the integral between 0 and infinite of f of t multiply exponential function up to minus st in the t. Now, in our case, f of t is sigma of t. We can see from here f of t equals sigma of t. This means this is extremely easy from math, no? To do basically the integral of exponential up to minus st. Why that? Because sigma of t, let me say, in the domain of the integration 0 plus infinite is 1. It is written here. I put it directly 1 because the integral in the context of the Laplace, or in the Laplace transform, is defined between 0 plus infinite. I think no problems to demonstrate, to calculate that the integral of exponential function up to minus st as primitive as 1 minus 1 or the 1 divided minus s, which multiply exponential function of minus st from math 1, I think this. Calculated between 0 and infinite. I don't know if you remember this. S is a parameter. You can say S is a parameter. It's a complex variable in the sense, a complex variable, yeah, and a number, no, but variable in our sense. But in the context of the integral is a parameter. The integral is in the time. At the end, I have this 1 divided s. This means, in accordance to this transformation, sigma of t is transformed into 1 divided s. We have this correspondence. Now, we can demonstrate that the Laplace transform of delta, the Laplace transform of delta is 1. The demonstration is a little bit complicated. This is boring. Here we have a little bit, let me say, a possible, how to say, intuition. And here, let me say, the demonstration using this partial integration or the partial integration rules. I don't want to insist this because probably you have seen these rules or the rule in, I think, math 1 or the math 2, but we can see the integral, we can demonstrate, which is when, again, the goal of this course is not to repeat exactly math. As I told you, we start from some knowledge of math to advance this knowledge in the system theory and control dynamics. Intuitively, never. You can look at these partial integration rules. It is I don't know if it's nice to see. This dot means the derivative. But let me say, intuitively, let me see if you can see from here a little bit intuitively why, let me say, this is what. But basically from the definition of delta, no? Because from here to here, I mean, do you remember I told you exactly now, no? delta of t multiply f of t is exactly this delta. Do you remember? Delta exactly in the morning today, in the morning, 10 minutes ago, I answered again the question. The student is not here today because I remember the name. The question about why I didn't put in the circuit delta multiply sigma, because delta multiply sigma equals delta. Before this exercise, I told you, if I remember well, delta multiply, I think so, because it was delta multiply exponential function equals delta. But in general, delta multiply f of t equals delta. This means if delta multiplies a function is equal delta, here we have a delta multiply this function here is equal delta. But the integral of delta is 1. Why that in the sense? Because we can consider the integral between minus infinite plus infinite. Doesn't change anything. I don't know if you consider this. Anyway, intuitively. And this means is 1. No? This is 1. Don't think about this. Think about this. Delta multiply exponential is delta. The integral between minus infinite plus infinite of delta is equal 1, which includes also the definition of Laplace. Of course, it's a little bit an intuition, but we can nevertheless consider this. No? Let me see if I can improve. This is not also I will use here another property which I don't have time to tell you. I mean, I'm using the concept that the integral of delta multiply exponential function m up to minus st is equals the function exponential function up to minus st calculated t equals 0. Why just at t equals 0? Because calculated at infinity 0, no? It's 0. This is a little bit, let me say, another property, a little bit more difficult to be demonstrated. From this expression included the integral to this one, a little bit intuitively, it's not so easy to see. But if you think that delta multiply exponential function up to minus st is delta, and let me say, roughly speaking, the integral of delta is equal 1. In the sense, no differences if I calculate I mean, the integral between minus infinite plus infinite includes also the Laplace transform in a sense. Or better say, the Laplace transform is included this. But anyway, it's of course a little bit intuitive. If you want to look at the mathematical, let me say, calculations is exactly calculated here. How we can see the idea now. Okay. The idea is why I told you that is included, because this function here is defined just at 0. Just at 0. This means I can extend. I don't know if this could be understandable. I can extend because delta is defined just at 0. But delta multiplied the function is the function delta. And this means also without now these calculations based on the rule which is here. The rule is here. Or we can reconsider starting from here. Okay, this one. Look at this important Laplace transform, or better to say the Laplace transform of an important function, which is the exponential function. We can see here, no? At the end, the exponential function. In general, alpha could be also complex, but let me consider real. Why that? But we have seen also complex. But in general, why this exponential function is important to be analyzed also with Laplace? Because I don't know if you remember, until now we have seen differential equation or differential equations and their solutions. We have seen that in linear cases, the exponential function represents this eigenfunction. No? Do you remember in math? This means it's basically the function which solves the differential equation. This means which represent our dynamics. And you remember the exponent could be real, but could be also complex. You remember, if we are complex, this was one of the last example which I did. If it's complex, this means we have oscillations. Remember, in the answer, in the signal, in the dynamics, let me say, roughly speaking. If the alpha is real, we have no, let me say, no oscillations. And then do you remember we discussed a little bit the stability in this sense. No? If the real part is positive, we have a system which is unstable because the answer or the behavior, let me say, or the signal in output is unlimited over time. If alpha is negative, we have an asymptotic stability. I told you about that. I will come back on this a little bit. And if alpha is 0, we have the system which is stable, because alpha 0 means a constant. This means the exponential function collapses in a constant, 1 particular. And then we can classify the system with respect to the answer, if it's stable or not stable, and so on. I will come back on this, even though I already told you a little bit. Now, in accordance with the definition, also, these calculations are easy, no? Are easy. Here is basically the results, and in accordance of the sign of alpha, we have the system stable or not stable, just analyzing this polynomial in the denominator. Now, very quickly, because we are not here for math, we will see now more in depth the stability and so on again. We can build in a table, starting from F. I can do the calculations, very boring calculation, because the integrals and not the derivative. Do you remember the integrals a little bit more complicated? But anyway, we have seen that the Laplace transform of delta equal 1, the Laplace transform of sigma equal 1 divided S, the Laplace transform of t 1 divided S square. We can do also this calculation. We can build this this table. What we have seen exactly now is this. What you have seen exactly now is this. But of course, believe me, in particular, think about this. I have an f of t, which is 1 minus exponential function up to minus alpha of the at. Remember, this we have seen the answer. This is the answer of we have seen last time of many systems, but last time we have seen an RC circuit. This is the answer of a step. I don't know if you remember this. I will come back on this in a few minutes. And this is the Laplace transform. Interesting also this one. I don't do because it's boring to do the integral of sine, but you did in math. I mean, it's not only the integral of sine. The integral of sine multiply the exponential function up to minus st. It's boring to do, but believe me, it's easy to do, even though boring. But we can use the work which the mathematicians did for us. No? And this is it's Laplace transform. Look at these two let me say, final expressions, which was exactly, you remember, the answer of this was an RLS circuit, an oscillating circuit. When I put an input step. Do you remember? We had this kind of solution at the end because we had complex eigenvalues of the characteristic polynomial. Probably we have seen in math. We can see here the real part, the imaginary part in the context of a real, and here it's Laplace transform. Let me go in depth with some examples. Here at this moment, I would like to skip this convolution product. I would like to skip this. It could be that I will come back later. Let me tell you about theorem 1. So it's theorem 2, also easy to do. And very important, the theorem 3. And then, the theorem 4 we can do also, even though it's not so very used. But anyway, sometimes. I would like to show you this 4 theorem, and then we will start with the concept of the transfer function and with an example. Exactly our let me say, standard example, which we have seen also last time. Probably I have some slides. This is better than here, but we can start here nevertheless. Okay, this is a little bit what I would like, an overview what I would like to do. Now, I repeated a little bit this table to conclude. As I told you, we don't need really to know, at least it could be that we don't need really to apply the back transformation. The reason is because very often we have just standard signals, and then means from f of s we can come back to the real signal, and this we will see the advantage of this. At this moment, it's not clear why it is important, this analysis in dynamical systems. At this moment, I did just a mathematical review about what we already know. At this moment, let me skip this, and let me introduce these 4 theorems, which can help to do some exercises, roughly speaking, because the theorem in math a little bit more articulated, formally, better organized. But let me see, I have a function f2, which is the derivative of a function f1. It's written here. Please pay attention, f1 of 0 equals 0 is an hypothesis. It's not necessarily exactly to have this hypothesis, but in the first formulation of the theorem can be used to simplify the I don't want to say the demonstration, but anyway, also the theorem itself. Or better to say, the formulation is more compact with this initial condition 0. Then, this is the theorem, the Laplace of f2 is s time the Laplace of f1. This means this sentence here can be rewritten in this form. f2 of s equal s multiply f1 of s. Very often the notation which we use is f capitalized of s as Laplace transform. F not capitalized of t is the corresponding time domain function. The demonstration, let me say, is easy somehow, but uses also this partial integration rule. This is a little bit, if you want to look at home, it's exactly is exactly the definition, the rule. Here, until here, in which v is exponential function up to minus st, u derivative is f1 derivative in our case, and then I can apply exactly This basically is, let me say, the Laplace transform on F2, the definition of the Laplace transform F2, in which we have to know the hypothesis, or we apply the hypothesis, in which F2 equals F1 derivative. And now apply this, believe me, apply or consider this position here, and better to say, applying this rule, we can derive the thesis. This means everything equal S multiply F1 of S, assuming that F1 at time 0 is 0. Assuming that F1 at time 0 is 0. If not 0, it's easy to see that we have here minus F1 of 0. No? It's not a problem, no? Because at time infinite, it's a 0. But at time 0, if F1 of 0 is not 0, remain minus F1 of 0. But very often, we are using this at least mathematically, to demonstrate this property, this property, this theorem, this hypothesis. Here, we will see later why. But could be also useful to know that if this is not included in the hypothesis F2 equals the derivative of F1 divided the derivative of F1 with respect to the time and this position here, and then we have this one. But if this is not guaranteed, we will see in some application the meaning of this. Why? Mathematical is okay. Why very often we don't consider the initial condition, or we put the initial condition 0. I will insist later a little bit. But anyway, if it's not 0, the theorem is changed in just including here minus F1 of 0. Look at we can see from here. Look at basically on this exercise, considering this rule in which v is exponential function m up to st minus st, and u derivative is f1 derivative. We can see here two forms of the notation. Dot is notation, apostrophe notation to indicate in the same form the derivative. Let me look if I forgot to say something. I don't think so. Look at them, but it's again an exercise which you already did the math. Therefore, it's not. I don't want to insist because it's not exactly the focus of our course. The theorem 2, let me say, is a dual theorem. Because in this case you have considered that F2 is not the derivative of F1, but is the integral of F1. We can see here. Again, here, excuse me, this is not equal. It's a LaTeX problem. Is semicolon or comma better, no? Comma. Here's not equal, excuse me. Again, as before, we are considering the initial condition 0. Then the Laplace transform of F2 equal 1 divided S, the Laplace transform of F1. The demonstration is quite similar as before. It's quite similar as before. Again, they say, I mean, the partial integration is also used here. We have in a different position, but anyway, once we are able to recognize the position, we can apply directly the rule. Let me see if I can comment a little bit more. Yeah, again is before, no? Again is before. Assuming that the f1 of 0 is equal to 0, this means t0, no? Here is equal. We have exactly mm, this results. Let me see if I can comment. I don't think so. No? I think we can now proceed directly. Hmm. Yeah. Um, this theorem here now. Final value theorem. This is very important. Why that? Because very often, as I told you at the beginning of the our exercise at the beginning of the semester, we have to analyze what happens steady state in dynamical system. Extremely important. What happens at time very large. This means also the stability, as I introduced intuitively, is in a behavior for T very large. What happens over time? Is going to zero. The answer, we say that the system is asymptotically stable. If it's going to a constant, we say that the system is stable. Properly, we consider, now we come back a little bit on this topic here, the impulse answer. No? But anyway, just roughly speaking at this moment. This means and a theorem which says that the limit of f of t for t towards infinite equals the limit of s multiply f of s for s equals 0 is a quite strong theorem because can be used to analyze the behavior of a signal. We will see the behavior of a system. We will see system and signals can be connected now in a few minutes. Here I reformulate using in a different notation. E is in a function, E of t, directly using the Laplace, which we will see we have many advantages. The demonstration is again extremely easy, just applying the definition of the Laplace of a derivative of a function. Why that? Why this inspiration here? Yeah, because we can see that the formulation of the theorem, recalls the derivative of f. Do you remember? The Laplace of the derivative of f is s multiply the Laplace of f. Again, let me come back to the theorem number 1. If you look at this theorem here, somehow the theorem 3, the final value theorem, is based on this, in which f2 is the derivative of f1. This means to demonstrate this sentence here, we will start with the definition of the Laplace transform of a derivative of a function f in this case. The calculation is extremely easy. I can put inside this limit because the integral is not in S. It's defined. It's undefined in the sense but between 0 and infinite, but in time. This means I can put the limit inside. I don't know if you remember math. Anyway, if you look at this, this limit is one, and then we obtain exactly let me say what we want to obtain, because this here is basically S multiply f of s. In accordance with the theorem 1, we called 1. This is exactly S multiply f of s, assuming that, again, that f of 0 is equal to 0. Excuse me, f derivative, no? F derivative is equal to 0 in this case. This function. We can see from here, no? F derivative at time 0 equals 0. This is the f derivative in our case. That is in fact, we can see here. Okay. Let me see if I can comment a little bit better. I think it's okay, no? It seems to be that here it's not necessarily to say that if one derivative at time 0 is 0. Why that? No, it's not necessary. Now I remember we can see also directly from here, because if this is the derivative of f1 at time 0 is not 0, we have here, do you remember, minus f no, it should be necessary. I think it should be. I have to check. Could be that both are necessary. F1 times 0 equals 0, and f of t at time 0 equals 0. Because from this integral, we have a limit of f of t minus f of 0, right? And here, in this part here, we have a minus f derivative of 0. Let me see if I remember well. No. F1, 0. This means we don't need anything. Again, excuse me for the error. I repeat, just in a second. Here we don't need any additional hypothesis, because this part here, if f of 0 not 0, we have here minus f of 0, but also here minus f of 0. This means independently, if f of 0 is 0 not, this holds. Okay. Again, to be more precise, I should add the hypothesis, but anyway, I didn't add because this is valid for each f at time 0. Because I have here minus f at time 0, but also I have here also minus f at time 0. This means I can cancel. This means independent of the value, it works. Excuse me for that. The theorem number 4 now is the dual theorem. Is also based on the theorem number 2. Why that? Because it seems to be. Look at this. That now I am using the initial value, or we can see here, the name is initial value theorem, here, final value theorem. Why the initial value theorem? Because we can calculate the initial value of a function ft. Initial value means at t to 0, or better to say 0 plus. You remember the concept of 0 plus and 0 minus? When t is going to 0 from the right part, which equals limit of s multiply f of s for s toward infinite. We will see probably in another context, we can use a different notation because E is a quite useful function to indicate the error. We will see in the control loop what I intend. I hope that I have time to tell you. The slide is conceived for another course, but anyway, it's a function, f of s or the e of s or f of t or the e of t, but in a particular notation in the control loop. Now, let me comment a little bit this, which is quite similar to this one, but I change, let me say the limit. Here, the limit is to 0, to analyze what happens in the infinite. Very useful theorem because we can look at the, let me say, at the steady state analysis. You know? Is what happens for L for T very large. Here, the formulation is the same, but we change the limit. S now is not toward 0, but toward infinite, and T toward 0 plus. This means it's going to 0 from the right. We can understand from the right because in the Laplace we are considering just the right part of the 0, let me say, concept. Let me see if I can comment a little bit. Sometimes it could be useful to look what happens at 0 plus. Remember, we have seen a little bit 0 plus and 0 minus. Here the demonstration basically is again similar, is done using the same concept of the partial integration rule, or the rules. I don't want to insist of this. This is basically a repetition of this part in order to have all calculations. Yes, the repetition. I mean, yeah, I am writing the limit for s toward infinite of the Laplace transform of f of s of t should be equal to this one. No? S, basically. Probably we can start from here if you want directly. Let me see if I find comment without doing the calculations, because also the calculation with this partial rule is a little bit boring in a sense. Yeah, I don't think so. It is necessary to. Here I forgot, nevertheless, to multiply by s. Here is there, but here is not there. And then I apply the partial the partial integral rule. Also here, no? Yeah, think about S, which multiply. Here is there, but here I forgot. It's here, we can see from here. Then using this rule, if you remember a little bit the rule which is before, we can see that this limit, but please put here S. I will improve the slide. Put here S, of course. S limit of the f of t, but for t toward 0. No? Let me see if on the right. Okay, because at the end of the calculation, we have this is 0, this is 0. Let me see if I can improve a little bit. I mean, this S will cancel with this SL will cancel with this. Why this is F plus? No? Because we can see, as I told you, the interval is on the right part of 0. At minus infinite is it's 0, but at 0 is exactly F at 0 on the right part, because we are on the right part. Minus is plus, therefore we have here. But please don't forget that here I forgot, I mean, don't forget that I forgot S here. No? S here. It's the same expression. Yes, the same, just in a repetition, as I told you, to have everything in one slide. Because this S here, I forgot to put here, excuse me. Sometimes LaTeX is not so easy to... It could be that this is not, yeah, because I thought I corrected. It's not exactly the last version of the presentation, because I think that I corrected. But anyway, just to show you a little bit this property, which can be useful in some context. Now, let me go ahead 5 minutes to introduce the concept of the transfer function, which is useful to do some exercise. And then we will stop, we take a rest a little bit, and then we will try to analyze in the context of Laplace, this example, which is a basic example, but extremely important, easy, but extremely important to understand. Look, do you remember the concept of the answer of the system? In particular, we have seen unit step answer, or in general, unit answer. We did also these calculations, also boring. We have seen the impulse answer. This was not so boring because we already calculated the unit answer. Do you remember? It was basically the derivative of the unit answer. No? The delta answer is the derivative of the unit answer. Yeah. What happens in general? If I have a u of t, we have a system, and I would like to calculate in the context of I would like to use in the context of Laplace the answer. This is a little bit the message of this slide. I don't want to go in depth on this convolution product. We will see a little bit later if I can tell you something about this. In any case, I can introduce a few words. This sentence here in the middle, let me say, in the lower part of the slide, in which we define y of s in accordance with this schematic representation of my answer. We have a u of t as a possible input, and we have u of y of t is an output. Here, again, we have an error in LaTeX. Here is u capitalized of s, y capitalized of S. And I have to correct, or I have to look for a better presentation. I have it. But anyway, I tell you, U of S in input, Y of S in output. As before, we have seen until now, U of T in input, Y of T in output. If I consider now the ratio between Y of S, which is here, instead of Y of T, capitalized, I told you, represent always, and in this context, mean at least the Laplace transformed of what? Of Y of T. Y of T is transformed as Y capitalized of S. Excuse me for this LaTeX error, also here. U capitalized of S represent the Laplace transform of U not capitalized of T. Now, if I consider the ratio between Y of S, which is the output in Laplace, and U of S, which is the input, which generates this output, we have the well-known, we have a new concept, which is a transfer function. Again, and then we will take a rest. I have a U of T, U not capitalized. It doesn't matter which one. It doesn't matter which one, which is going through the system. At this moment, forget this expression here. We will obtain a Y not capitalized of T. Now, think in different form. We can consider the Laplace transform of U not capitalized of T, and thinking about an U capitalized of S, excuse me for the error, which generates an Y capitalized of S, which is the Laplace transform of Y of T, Y not capitalized. If you consider Y capitalized of S divided U capitalized of S, we have a new structure, a new element, which we call transfer function. The ratio between the effect in Laplace and the cause in Laplace. The ratio between the output of the system in Laplace divided the input of the system in Laplace transform. We will see how is important this in the context of an exercise. Let me say also exam exercise, why not? It could be that I look if I have some manuscripts, because in the manuscript, I suppose I have something more, some more considerations, analysis with respect to what I have in the slide. But then, nevertheless, you can consider also at home the slide that in particular, look at this slide here, is exactly what I told you until now, in which G of S is calculated. We will do by hand. Also, it is also done here by hand. Right? But I think by hand with the slide, with the manuscript, which I should find now. And we will see this correspondence in terms of Laplace. And interesting, because in this domain, we can consider again the answer, but for our specific input in the context of Laplace. We will see how easy it is to calculate the answer if I have some inputs, in particular this input here, but more important is here because we will see that the transfer function basically represents the Laplace transform of the impulse answer. The Laplace transform of the impulse answer. Yeah, I think I told you now everything. Let me stop here. We take a rest. I try to find the material because I think is more detailed what I have in my manuscript. But of course, you can read also. You can scroll down also here at home. Yeah, let me stop here at this moment. We take a rest a little bit. 50 minutes, 20 minutes, just the time to find the material to do this exam exercise. Basically, the response. I don't know if I have in any case, I think I have the step response. But anyway, the idea is to calculate the transfer function, which is the impulse answer. And then the step answer. In the using let me say, the Laplace domain, but we will repeat again the concept of the transfer function. Let me say 5 past 10, we will meet here again. See you in 50 minutes. As I told you, I found the the newest presentation with these corrections. Do you remember I told you S, I forgot at the beginning, but then at the end is correct. I mean, the results are all correct, but there's some small error in the sense, refuse, we say, that's something that in LaTeX, I don't know if you know LaTeX, is somehow geblieben in the code. This is not printed or printed wrongly or erroneously in the effect during the compilation and so on. But I have it. I will upload with the correct in the sense with formal correct, because the results are correct. The results are correct in any case. Okay. Let me now analyze using the manuscript. This. The exercise or in a part of exercise which we did last time, but using the Laplace approach. The Laplace approach. I speak approach because we will see what I intend, but based on math, which you already know from Math 1 or the Math 2. And today, I really very quickly, nevertheless, recalled for you. Okay, look at this. We have here again, because we will use not only this, but basically this, not only this, but just to recall a very important Laplace transform, and the Laplace transform of what? Of an exponential function multiplies sigma. You remember I told you this is extremely important because we have seen until now that the exponential function characterizes the solution of a differential equation. What is the meaning of differential equation in dynamical system? The meaning is that the dynamics, let me say the movements, the trajectories of the systems, or let me say the behavior of the systems, linear systems, are always characterized by the exponential functions, always characterized. This is a little bit what I told you quickly, what you know basically from math. This sigma is formally there, no particular meaning because the integral is defined between 0 is plus infinite. This means this is 1. It's formally there, but for us means, you remember that I told you, or reflects exactly this part of the scheme, which is here, which basically includes, the scheme includes the switch. Of course, we can also omit, but just to understand a little bit formally what this sigma can represent. We have already seen also last time in time. The exercise is, I think, I consider this. No? I consider. Let me go ahead now with the exercise. I connected this input with its switch to the RC circuit. Therefore, I told you can look also what we have in the presentation. But of course, this information in the presentation could be done, of course. But sometimes my opinion is more useful to discuss here because it's more. I can indicate, I can correct, I can add. Very often when the students are here in the presence, it's a shame it's not the case of today. They ask me and then I can add something. In the slide, we don't have this flexibility. Therefore, the slide, I use the slide to to tell you a little bit the concepts, and then we will always, we switch always in manuscript. Anyway, the problem is quite no, it's exactly in this picture. The picture is exactly what I told you last time. At time 0 is going to 0, and then the idea is the question is to calculate, for instance, what happens. What happens means to calculate UC of t. Let me consider is written here the initial condition of the capacitor at 2 volts and the input 1. You input equal 1, and then of course, if I consider the input together with the switch, we have a 1 or U input, doesn't matter what, 12. Remember, last time we have seen 12. I am changing just to change, but 1 of 12 does not change qualitatively the solution, change just quantitatively. Multiply sigma. The meaning is at time 0, I am starting. Look at this. If you remember the theorem 1, the derivative theorem, remember the derivative theorem, I recall for you here. And this hypothesis here, do you remember I insisted a little bit, not much, but I insisted a little bit on this. We have this. We will see a little bit, I think in this part, I don't know, because, yeah, in this part. Because, yeah, this example is interesting example because it's easy, is in the sense, the examples in linear system is almost the same. Once we have seen example, order one state variable. Here the state variable is the voltage of the capacitor. When we have seen a system with 2 states in which we can have also oscillations, all systems can be considered as a combination or cascaded or consisting of some dynamics of first and the second order combined together. But of course, it's a little bit boring, the calculation. But at this moment, we have seen both first order and second order. Let me go ahead here. This means this didactically to discuss some important dynamics, some important dynamical aspects, extremely effective in my way. Look, the derivative of UC in time can be seen in this form here. Please pay attention. Now, I included this. Do you remember f of 0? Do you remember, as I told you before, f of 0? Because of this. Do you remember I told you, typically the mathematician, or in general, in order to, yeah, I don't want to simplify because nevertheless, I show you in the theorem that is not the problem. For another reason, we will see that we consider, we present the theorem with f of 0 equals 0. But of course, as I told you, if it's not 0, as in our case, we have to consider it. This is 2 volts. We will see the meaning now that this initial condition, let me say, now we can say initial condition, characterizes what? You remember what we have seen until now? The free answer. Characterizes the free answer. Very often, why we, in the theorem itself, we find f0 equals 0, or here u of 0 equals 0, because we will see that we consider in Laplace just the fourth answer, and we will see why. But in any case, no problems to include what happens before 0. Before 0. You remember, until now we have seen something more in detail, 0 plus, 0 minus. But let me, at this moment, go ahead directly with this approach, and then we will discuss also this. Look, without this L, we have here voltage in input, assuming that is exactly this structure here. This means U input of t sigma of t. This means that this expression here includes also somehow 0 minus 0 plus. This expression, please pay attention to this sentence, includes 0 minus 0 plus, because sigma is defined over 0 minus 0 plus, because a 0 minus is 0, a 0 plus is 1. To be precise, at 0 is 1. This means it's fully defined. This voltage here equals this balance, Kirchhoff. We have seen, I don't need to explain this. No? This is the derivative. Dot is the derivative. Sometimes in some book you find apostrophe. Sometimes as here, D with a T. I use all possible notations. Then, I did insist today, but last time I told you the Laplace transform is a linear transform because of the integral. Now, do you remember? Because of the integral. In any case, independent of linear or non-linear, I can say the Laplace of the left part equal the Laplace of the right part. Let me say so. And then I use the linearity, distributing the transformation, the transform on these two elements. I mean, the Laplace transform of this signal here is 1 divided S. Now, in the demonstration of the theorem, we don't have sigma, but as I told you, sigma is defined, is 1 between 0 and plus infinite. This means does not change the Laplace transform. Again, this is 1. No? I mean, I can associate always at each signal. It doesn't matter which signal I have here. Here, for instance, it seems yeah, that I can consider also another signal. I don't know if I have the example, probably yes. Let me see. I don't know. Anyway, I can consider this with its Laplace transform. If I consider 1, this is the Laplace transform. Because sigma inside the Laplace structure between 0 and plus infinite is 1. No? But states formally the steps. In any case, in this form here, we include 0 minus 0 plus. 1 divided S, and then look at this. RC inside the integral of the transform go out of the integral. This means S multiply UC of S. Because S states exactly the derivative of, or reflects the derivative of this function here inside the integral, which is basically the base of the Laplace transform. Anyway, the Laplace transform of UC derivative is S, U capitalized C of S minus this, because I am assumed that the initial condition is not 0. And the theorem works, but of course we have to consider this. RC is multiplied because I can distribute RC. Plus this. Now, from here, I can calculate exactly UC of S, what I want. You remember, the final goal is to calculate UC of T. The final goal is to calculate UC of T, but using the Laplace tool. But we can see that this tool is already a big advantage. UC, do you remember, consists of 3 answers, 4 answers. I told you these concepts from the beginning of the semester. 3 answers, 4th answer, and so on. Now, the advantage which we have in the context of Laplace, the first advantage which is visible from here, is directly visible from here, that I don't need to solve the differential equations. We can see that the differential equation, this relative easy differential equation, disappears thanks to the transformation of Laplace. We can see here just an algebraic expression in S, meaning 1 divided S, I can consider UC of S here, and here I can write everything in this form, minus LC of UC at time 0. Now look, UC of S can be written in this form. UC of S equals what? This divided S divided this algebra. This is just algebra. Plus, yeah, here is a little bit difficult to see the calculations, but it's so not extremely let me say difficult to see, because yeah, if you bring this on the other side, we have a plus LC UC 0. Then I divide it, let me say, this element by this, and I have this, and I have this. And then I divide this element by this, I have this. Here I put S divided S that you don't need to put. I don't know, it's clear. I bring this on the left part. Let me say left part, on the other part. The idea is to isolate UC of S. And then, in order to isolate UC of S, I have to divide everything by this one. And believe me, it's easy to see. We have 1 divided S and divided this. And then we have LC UC of 0 divided again this denominator. Now, we can see here a little bit, again, directly, without many considerations, as we did in time, that this part here, but let me start from this, if you will. Let me start from this. Probably, anyway, it doesn't matter. Probably it's better from this. This part here represents the fourth answer with respect to the sigma. Because 1 divided S, it could be that I have a better expression. It's just basically the calculations are the same, because yeah, and a student asked me something, I show you, I read it everything, but we can express also directly here. Would be better now. Yeah, I show you better later. Just roughly at this moment. We will see later more in detail that this part here represents the fourth answer with respect, or better, considering the step. Why that? Because here we have the step. We will see later how I can, using the back transformation, but it's not so difficult to see. It's not so difficult to see that this can be seen as the transform of the signal here. And this can be seen this here as the Laplace transform of this signal here. In which UC of 0 is 0,5. Let me show you quickly with the table, and then we will redo quickly the calculation, and we will see how we can let me see, consider this. Why the back transformation of this is this one? I can write this in this form. I can write this in this form, in which you remember R multiply C is equal 1, you see 0.5 here, but very important this here. Believe me, it's easy to see that this expression here can be written in this form. Now, if you go back to the table, let me go back. Yeah, I don't know if it's visible in OPS. Which back transformation I have to use? It's this one. The structure, here we have an error, is S. A divided S multiply parenthesis S plus A. Excuse me, this might no sense A plus A. Again, LaTeX, no? S plus A. And the back transformation is this one. Now, in our case, A is 1 divided RC. Please pay attention here. Is S. A is correct here. A is correct here, but this is S. It's a shame also, this error. Like here, no? Excuse me, the first A is S. Now, coming back to our calculations. Our A is 1 divided RC. Do you remember it was A, S, parenthesis, S, this is wrong. Yeah, instead of S, I wrote A, plus A. And we have seen that we have 1 minus exponential function minus A, t, in which A is in our case 1 divided S, the fourth answer. With respect to sigma, please pay attention. In the table, you can see everywhere sigma. Why that? Because sigma is defined exactly inside the domain of the definition of the Laplace. In our case, makes formally sense because of this switch, and moreover, the sigma includes in itself the concept of 0 minus 0 plus. Now we will go in depth in the next page. It's quite similar. We have a value. This is 1, R multiply C in accordance. I can put whatever I want. If it's 10, this is 10. If it's 2, is 2, because in the constant, this means and the Laplace doesn't play any role, because I can put in front of the integral, let me say. Here is 0.5. Here I can do the same calculation. You can see here. I can divide everything by RC. I will disappear RC here, and I have here S plus A, or the alpha, I don't remember what. And the back transformation is UC of 0, exponential function here. Excuse me, sometimes I write exponent is, it would be better in the sense exponent. Excuse me, I forgot to exponential function. Multiply sigma. Sigma can be also included for the reason which I told you before. Let me show you in the table where this is. Doesn't matter which constant I have, because the constant in the Laplace is, let me say, comes in front, let me say, before the integral. Let me show you. Here. No, here is correctly represented. 1, but this is 0.5, doesn't matter, I have here in front 0.5, divided S plus A. And we have minus A multiplied T in the exponent. E or the X books, you can find both. But of course, you can include always here sigma, everywhere, believe me, everywhere. In our case, it's extremely important, sigma, because we have typically in techniques, in engineers, we have a switching. We have to distinguish between 0 plus and 0 minus, or 0 minus 0 plus. The mathematicians, this came from a book of math. The mathematicians don't have this necessity to distinguish. between 0 minus 0 plus, or at least the mathematician who is working in engineering, of course, yes. But in general, we don't need. But you can include because does not change the results. Because sigma again is defined between everywhere somehow, no? Yeah. And this includes also this 0 minus 0 plus. Does not change everywhere, but before 0 is 0. Therefore, is match with the definition of Laplace. Free answer for answer without considering anything about differential equations. Let me see if I forgot here to say something. Otherwise, we can. Okay, but I think I already analyzed very well. Nevertheless, let me, because students ask me to go more in depth on this. Let me do together. Therefore, this was done in the lecture after this slide here. It's the same exercise here, the same exercise. It's not exponential function, no, it's just the same as exercise. It's the step answer. Moreover, unit step answer. But I repeat it again a little bit. I don't need probably now, but look here, I introduce a little bit some possible discussions. UC 0 minus is equal UC 0 plus. You remember we discussed a lot about this in time. Now, let me see with this approach what we can see. Again, Kirchhoff, I don't need now to go in depth. Laplace of right, Laplace of left. In the other slide, I was a little bit faster, but I think no problems. Yeah, inside we have also, as I told you before, the Kirchhoff balance. This voltage is equal to this balance here, and then I do the Laplace. You can see here if you want. You remember here before I was a little bit faster, in which I considered the current equals C multiply the derivative of UC of t. Do you remember? Here you can passing through on the current because the students ask me that it was too fast, no? But the results at the end are the same. Now we can see here because if you transform the current in Laplace in U C of Laplace, we have exactly C multiply S UC of S. Because the current is C times the derivative of the voltage. The day before or the lecture before, I wrote here directly C multiply UC derivative. Anyway, if you don't like, you can do in this form. The current in Laplace, the current of the capacitor in Laplace is C times S multiply UC of S, no, U capitalize of S. And at the end, please pay attention. We have exactly the same. S of S divided S does make sense. It makes sense. It's not wrong, but it's useless. This we had. Remember, I divided everything by RC. Now, page number 3. Where is the page number 3? to find. I find. Excuse me. To go a little bit more in depth with the calculation and with some considerations. This is exactly what I have for UCOS, considering this position here, no? R multiply C equal 1. No? In particular, I put here R equal 1 and C equal 1. I have this expression, which came from this, which is exactly from this, which is exactly what I did the lecture before, or better to say for today, the slide before, the slide number 1. Now, how I can demonstrate a little bit more explicitly the expression in time. I don't know if you remember math. This is clear what is directly from the table. This is clear what is directly from the table. Of course, you say to me, but you explain to us that direct from the table. I can calculate, I can see how it looks like the back transformation of this. Yes, of course, but you can also calculate it a little bit more explicitly. That is the effect, let me say, of the transform of the Laplace transform of the fourth answer related to the sigma. Why that? Because if you consider this expression here, which is this one, in this form, and you calculate A and B, you look here. This expression here is equivalent to this one. I don't know if it's visible. The idea is to, what is the idea? The idea is to isolate, let me say, the effect of sigma and the effect of sigma, possible to say, we in the system, let me say. In any case, I would like to mathematically to have a decomposition of elementary elements. Let me assume this. This expression is equivalent to this because I can multiply left and right by this. Therefore, I have here A multiply S plus 1, because S and S I can cancel. Again, I multiply left and right by S multiply parenthesis S plus 1. I will have A multiply S plus 1 plus B multiply S. Try to do at home to multiply left and right by S parenthesis S plus 1 parenthesis. I will have this one here. Now, this expression here can be written in this form here. I can separate everything which depends, which is multiplied by S, and in this sense plus everything which does not is multiplied by S. And then I can see that I can find A and B which satisfies this equation here. It is enough to put A equal 1 and B equal minus 1. Why that? Because the component of S on the left part is multiplied by 0. I can write here 1 plus 0 multiply S. This means this must be 0. And what about A? Must be 1. This means A equal 1, and A plus B equals 0 implies B minus 1. I think you are able to do these calculations. And exactly, I can now see more explicitly the fourth answer and the free answer, because the back transformation of this is sigma. The back transformation of this is minus exponential function up to minus 1t multiply sigma. Of course, you told me, but I already had this in the table. Yeah, but here we can see a little bit better these effects. You remember in the fourth answer we have this component which is reflecting the free answer. You remember, if you remember in time my analysis, just to go a little bit more in depth, the result is the same, of course, as before, which can be written if I if I consider these two elements. Now again, the answer is the free answer plus the fourth answer. And we have something like that. Before 0 is in a constant 0.5 volts, and then I'm going in accordance with this equation. Because this equation here holds, excuse me, for t larger than 0, no? Larger than equals 0, the balance holds when I close for t grows larger or equal 0. No? I don't know, probably I forgot to tell you explicitly, but it's here. No? But it was always here also in the example last week in time. Now, as I told you in Laplace, we don't have to distinguish at the beginning between 0 minus 0 plus. There is a little bit implicit inside in S because the Laplace frozen the time. The time disappeared, is inside the definition of Laplace. And from this equation here, we can see now that we can answer the question. Which question? The question here, as I told you before, is UC 0 minus equals to UC 0 plus? With the calculations. And then, because the Laplace approach includes in itself the time, I frozen the time, includes in itself the time. We can see exactly that U0 minus U0 plus from the graphics, quite clear, but also from here. No? A 0 minus, we had 0.5, appeared also from here. A 0 plus, we have again 0.5. Because of the structure of the solution in time, which came from Laplace, which includes in itself, excuse me, the time. Let me see if I can told you something more. I don't need to explain here. I need to call one second. Here everything is calculated as before. You remember last time we calculated the current during C times equal 1, the derivative of this. No? Doing the derivative of this. This means 0 And then we have a function which is starting from a constant. We calculate it. This is enough to do the calculate the derivative of this. No? At 0 plus is going to 0. Now, do you remember delta, which we have? We can simplify. I don't know if you remember. No? I don't need to redo. The derivative here is 0, and derivative here, if you do this, we did this this derivative. We have the 2 delta which have we have the delta which multiply this and multiply this, but they cancel. I don't know if you remember. And then remains plus 0 plus 0, comma 5, multiply this exponential function up to minus t, multiply sigma. This means the current is 0. Let me calculate. Let me take the new slide. I have to calculate this, then I stop 5 minutes to call, and then I come back. 1 second, okay. Let me write page 3A. I will scan for you. No? Calculate current of let me write explain. In the slide before, I write E as you want. It's not also in the examination is not important. You remember C times the derivative of this. We have seen last time. No? Meaning, excuse me, calculations. Then we will see the meaning. The derivative with respect to this one plus the derivative of this inside is 0 minus 0, 5, which become plus because of this minus here, exponent of minus t multiply sigma. Why this is 0? Because this function multiply delta is delta. Remember, I told you at the beginning of today. Because of the definition of delta. This implies 1 minus 0, 5 exponential up to minus t multiply delta of t is equal to 0. And this implies that EC of t is equal, C is equal 1. Remember, just to simplify the calculations, also in the exam, I didn't put strange number. At the end, it could have some strange number, but at least at the beginning, we start with good number. meaning, interpretation, also meaning, whatever. It means something like that. 0 until here, and then we have something like that. It's going to 0 at infinite time, no? In infinite time. right? We can see that UC 0 minus not equal UC 0 plus. We have seen also last time. Huh? Because it's just the partial derivative, in partial derivative, just for t larger than 0. Excuse me. Yeah, for t larger than equal 0. No? Less than 0, we have to do the derivative of the constant. Which is 0. Now, I have to call because otherwise too late for me. I open for you another exercise introducing again the concept of the transfer function. Always the same concept. In which UE is delta. The idea is please calculate, it's not written, but it's written here. Calculate UA in case we have a delta. We don't need sigma because I told you sigma multiplied delta is sigma, no, as always. And now we will see more in depth the meaning of the transfer function. The transfer function basically is independent, please pay attention, dependent on the input. Because I normalize by the input. It's always this. We have seen also before. I mean, before was 1 and 1 here. Now I put the different value in order to have a different value. It doesn't matter now to show that we can do calculations, general calculations. Here, the initial condition is 0. No? Therefore, we are just considering the fourth answer. And this is a little bit the meaning of the transfer function. The transfer function is associated basically to the fourth answer, but can be used also as, in general, as we have seen until now, let me say, for the total answer, fourth and free. Now, to emphasize again the transfer function, the transfer function is something which does not depend on the input, because I normalize by the input, but directly is the, if I do the back transformation, the transfer function, this is the, how possible to say, the impulse answer. No? I have to call really quickly, look, the question is calculate voltage here in case exactly we have this one. But it's not difficult because the Laplace of this is 1. Therefore, I told you that the transfer function is the answer or the response to the unit, let me say, inputs, because the Laplace is 1. I mean, if UE is in the delta, if UE is in the delta, remember, the transfer function UA divided UE. If it's this in the delta, I can put here UE in order to calculate UA. The idea is to calculate UA of t passing through or using UA of S. Think about this. I come back in 5 minutes and we will go ahead with this concept here to connect the transfer function with the delta or the answer, the impulse answer. And we will come back on this concept here, and then we will do the calculation. But the calculation is already here. It's the fourth answer considering the delta and input. Of course, if we don't have initial conditions, if the initial condition is 0. This very often is an hypothesis because we consider just the fourth answer with the transfer, with the transfer function, but can be used, as you've seen before, considering the free answer, this means initial condition. We have seen also last time in time how we can calculate the impulse answer also with an initial condition. You remember? Do you remember? We have seen. Okay, give me 5 minutes. I come back. Let me stop here. Yeah, let me start from here. Again, I would like to emphasize with this slide how strong is this approach. And now we focalize a little bit more on the transfer function, which is exactly this here with this value here. Before was, you remember, 1 divided S plus 1. Let me come back in order to justify a little bit better this. Because probably I did a little bit too fast. Yeah, it's probably it's not so, let me say, easy to be seen. The transfer function, as I told you, is as definition. If you look, let me coming back. This is nice to repeat because it's important. The transfer function, in its original definition, is related to the fourth answer, but again can be used also to calculate the free answer, in this sense also the total. Look, G of S, which is Y of S divided U of S capitalized, is something which does not depend on you. We can see from here, because I divided basically Y of S divided U of S. Basically, it's the ratio between output and input. Meaning, in this case, let me consider UC of 0 equals 0. This is not it. This is not it. RC, R multiplies equal 1, R multiplies is equal 1. What is the transfer function here? The transfer function is 1 divided S plus 1 if R multiplies is 1. Why that? Because 1 divided S can be seen as the Laplace transform of the input in our case, which is in a step, the input. This means if I divided this UC of S divided 1 divided S, I have the output divided the input. But it doesn't matter which kind of input I have. It doesn't matter which kind of input I have. If I have a ramp in input, I have here 1 divided S squared. But the transfer function is the ratio between the output divided the input. This means I divided this case by 1 divided S squared. It doesn't matter which input I have. It does not depend on the input. I don't know if this is clear. Can be calculated for each input. But properly, if this is the transfer function, we can see that is the Laplace transform of the impulse answer, because the Laplace transform of the impulse is 1. Exactly what I wrote here. This means that we can say that the transfer function, or any transfer function, is the Laplace transform of the impulse response. But, as I told you quickly, is independent of the input. Can be calculated for each kind of input. I already a little bit sketched what happens for this voltage here in this case. It's quite similar, I would like to say the same as the current in case of the step answer. But why that? Do you remember last time we have seen that the impulse answer is the derivative of the step answer. But what is here is quite similar because the current is the derivative of the voltage in the capacitance. I don't know if it's clear. Here I would like to calculate what is the voltage if I have an input, the delta, in the unit impulse. You remember, we calculated exactly before what is the voltage if the input is the sigma, the step. In this case, the output is the derivative of the sigma answer, which is this one. Before was the current, now is the voltage. In this case, we can see that 0 minus is not 0 plus. Without doing this consideration as last time, a little bit complicated, here can be seen very well. Why that? Because the Laplace transform at in itself, the time enclosed. This means also, therefore, is extremely important to analyze the system in Laplace domain or the Laplace, let me say, frame. But the system must be linear. Again, the system must be linear. Otherwise, I cannot use exactly what I told you, this distributive property and so on. Basically, this answer here is the derivative of the step answer, as we seen last time. Now we have seen directly in Laplace frame or Laplace domain, let me say, or Laplace approach. Again, please keep in mind this sentence here. Properly, we can say that the Laplace, the transfer function is the Laplace transform of the input answer of the response. We can see directly from here, but can be calculated. It's always the same for each kind of input because it's always the output divided the input. Laplace, of course, input form. Here I didn't wrote, but it's clear. If this is 0, very often, not very often, we don't need to define the Laplace transform this element here, because it's already here. For each input, they say 1 if R multiplies this is 1, 1 if R multiplies this is 1, and here we have 1 divided S because we considered the step. But if you consider, you look at the step, look at the table. 1 divided the square, which is the transform, the Laplace transform of the ramp. If you divide it for 1 divided square, we have always the same. Okay. This we already did. In case of 1 divided S plus 1, doesn't change anything. Just these two values. You have to calculate the Laplace, the back transform of this, which can be calculated in this form here if I am able to calculate A and B. You remember this decomposition. Again, we have seen before for a different value, but no problems now to redo the same calculation. Probably we did in math, no? such like that when we have a fractional function, in which we have A equal 1, B equal minus 1. A equal 1, B equal minus 1. Do we do the algebraic calculation? We don't need here really to explain, I think. No? I think that is no from math. Of course, I can directly look on the table. No? I can directly look on the table. But so we can explicitly see a little bit more in detail what happens. Sigma, and this is -1, which multiply exponential function, or the e if you want, up to -0, 1t. Do you remember minus alpha or the minus a? No? Multiply sigma again. Sigma is still there, no? Always there in the sense in our context, because we are analyzing something related to circuits or system which starts its dynamics at time 0. We already know this, but in this case, it's just a forced answer, no? Because we don't have any other elements. Typically, the transfer function, if we are not specified the initial conditions, if the analysis through the transfer function, if the analysis through Laplace is with initial condition 0, this means it's related to the forced answer, but can be used, and we have seen exactly at the beginning also, for the total answer. This means includes the free answer. That is, we have seen before, but not starting from 0, starting from the initial condition, but no essential differences, no, we can say. In this case, the voltage on the capacitor that's 0 minus is equal to the voltage of the capacitor 0 plus. As before, when we started from 5 volts. Structurally, that don't change. Qualitatively, does not change. We can use also the transfer function, as I did before, or the Laplace approach, but the transfer function, in any case, also, if we have initial conditions. Let me see if I forgot to say something. I don't think so. This means slowly we can close. And next week we have 2 hours. We will go a little bit in depth with convolutions product. Then I do another exercise with Laplace. And after next week, we will analyze the dynamics of the controllers. 1 second. I think I told you everything. I hope it was not so boring today. We are on track. Again, this week, convolution products, special aspect, but no, I will upload the corrected refuses, which I found irrelevant for the results. And then after next week, I hope to be here, but I will communicate. Anyway, we have time. We have time to show you some aspects of the dynamics of a controlled system. Okay, if you have questions, I'm here. Otherwise, I will upload this material here. It's quite interesting, in my opinion. And I will re-upload this new version of the presentation, even though this is irrelevant. It's the 2 errors, but just in 1 point, and then it's corrected later. Thank you. I'm here after stopping the lecture.